Hello everyone, let us get back to lecture number 6. And today we will get to the phase diagram from the point of thermodynamic consideration. Last two lectures we talked about drawing phase diagram from cooling curve, and actually we have drawn an eutectic phase diagram where this is my T eutectic and this composition is X B eutectic, and this is 100% A and this is 100% B, and this is temperature axis, this is percentage of B. So, this was drawn from with the use of cooling curve, and that time some of the informations are obtained. For example, transformation temperature, like TMA, TMB, which are the melting point of pure A and pure B, and also T eutectic, the eutectic temperature, and also we can get the information of compositions of alpha, liquid and beta at different positions. Different positions means as per the temperature and composition. For example, if I try to take this composition which is X0, then at this point first solid would appear and that solid would have composition which is here, and then the solid amount would be very small, but the liquid amount would be decided by the lever rule, which is this much amount of liquid would be there. Now, as we go down and then we will see that at different points we get different fraction of alpha phase as well as its composition, and correspondingly the liquid fraction and composition are also changing. For example, if we consider this particular tie line, I could see that alpha would have composition at this point and the liquid would have composition at this point, but the liquid fraction would be this much and solid fraction would be this much. So, like that way we will reach to that point of eutectic temperature where the remaining liquid, this much liquid, will convert into alpha and beta as per the eutectic reaction, liquid converting alpha plus beta, and this much amount would be alpha, and that alpha would have a name called pro-eutectic alpha. So, this amount would be alpha pro-eutectic, and this much liquid will get to this particular transformation. Now, once I reach here, I will also find out what will be the composition of alpha and beta, and here the composition of beta would be this much and the amount of beta would be this. This is the fraction of percentage of beta, and of course, this is basically coming from weight fraction, and then this is my alpha percent, and since tie line is based on mass conservation, so these are basically weight fractions. And beta would have composition this of this amount, and alpha would have composition this. So, like that way, at different points I could get to know what are the phases coming up, and at the same time what are the composition as well as fraction of those transformation products. But during heat treatment we need to know TTT diagram. So, that would decide my time temperature, means how long I would like to continue heat treatment and at what temperature we need to do the heat treatment, depending on what sort of properties we would like to get from the final product. So, that will be decided by TTT or CCT, but in both the cases I need to know I as well as U or V, which are my nucleation rate as well as growth rate respectively. Now, in order to know I and V, we also need to know few other things. One is interfacial energy, which is gamma, then free energy change, which is driving force for the transformation, and when we consider the free energy change, I need to have two more information. One is overall free energy change, that means for overall transformation kinetics, which is decided by JKMA equation, x equal to 1 minus exponential minus kT to the power n. So, that time we need to know the overall free energy change, and it should be negative to have the transformation possible. And another term which is there, which is termed as delta Z0, another term which is there, which is called delta Gn, which is the nucleation driving force or nucleation free energy change. Now, these two quantity we cannot get from this diagram if we have this diagram from cooling curve. So, for that reason we need to get to thermodynamics, and we need to know free energy versus X plot for alloy system, and in case of pure metal system or pure system, that time we need to know G versus T plot or G versus P plot, which is the pressure. So, now in order to know these things, we need to also get to the basic data, thermodynamic data. In one case, for example, in this case we need to know Cp of that metal, as well as in this case we need to know the molar volume change with pressure, and in this case we need to know the chemical potential change with temperature, and that time we keep pressure constant if it is a condensed system. Now, since we will be handling with condensed system for our heat treatment purpose, so we would be looking into the chemical potential data, then Cp data as well as molar volume data of the metals. Now, coming to this G versus X and X means mole fraction. Now, we understand that in order to know this free energy change for nucleation, which is part of nucleation rate, and overall free energy change, which is part of overall transformation kinetics, we need to have idea how to get to this particular G versus X plot. And whenever we get to the mole fraction, now we are considering the binary system. Because if we go to the ternary system, things will get complex. So, let us confine to a simple system which is binary. And in case of binary system, we can, and whenever we talk about binary system, we generally consider solution in the beginning. There could be formation of compounds, but let us keep it aside for the time being. We will just consider solution, and that time we would consider that solution means it could be liquid solution, it could be solid solution of two elements. Let us consider element A and element B, and they are pure in the beginning before they mix and form solution, and we are assuming in the beginning that they have same crystal structure. Same crystal structure, and when they mix they form the same crystal structure again. So, these are some of the assumptions. The another assumptions we take that A and B can be mixed over the entire composition range. That means, the solution could vary from 0% A to 100% A. So, entire range we can constitute a solution, either it could be liquid solution or solid solution. Now, when we consider this, we consider that these are condensed system. We are not looking into the solution formed by gases, because we will be treating steel as well as aluminum alloys, which are condensed, a solid state, as well as sometimes we have to also get into the liquid state, for example, casting. Now, when we do that, when we treat this solution, again there could be possibility of two types of solution. One could be ideal, another could be non-ideal. Generally, in case of ideal system, if we put it in terms of thermodynamic quantity or thermodynamic variables, we say that del H mix equal to 0. This is a kind of thermodynamic statement we can say, and here we say that del H mix can have non-zero values, which could be less than 0 or greater than 0, depending on the interaction between the atoms of element A and B. These elements can attract each other, A atom can attract B atom or A atom can repel B atom. So, depending on the situation, we can have values of del H mix which could be negative and which could be positive too. So, we will get to that particular part again later, because handling non-ideal solution is little tricky. So, first let us get into a much simpler situation, which is ideal solution, and that time we say that del H mix equal to 0. Now, we have to also physically visualize what is this ideal solution. What do you mean by del H mix? So, del H mix 0 means the interaction between the atoms of opposite character, means A and B, two different elements, their atoms, they do not like to interact each other, but at the same time they would like to form solution. means that they do not have any attractive or repulsive nature. So, in order to visualize this, let us also take example from gas and then we will get back to the solution. Now, if we consider a gaseous mixture, if A and B, let us say two different gases, let us say one gas is M, another gas is N, these two gases are there, let us say they are monoatomic gases. Now, if we mix them at a low pressure, very low pressure, how do we attain low pressure? Let us say we fix the component mass, let us say the amount of that gases if we fix them. One way to, and also if we fix the temperature, one way to achieve low pressure is if we can increase the volume. And if we increase the volume, then amount of, that means it is a control volume, the amount of metal this gas atoms are fixed already. Now, if we expand those gases, because you are increasing the volume, the gases will expand and it will try to occupy the entire volume. So, its pressure is going down. Now, if the pressure goes down, then interaction, this atom-atom interaction is becoming very minimal, and that we can consider as an ideal solution. Similarly, in case of liquid solution, let us say, if we have a glass of water and then if we mix some second solute, if we have water which is as a solvent and if we add some solute, and that case if the amount of solute is so low, infinitesimally small, then also we can say the interaction between solute atom or molecule as well as water molecule would be minimal, and we can consider that condition to be negligible interaction. We can say that it is ideal solution. Ideal solution, and that time it is infinite dilution. This is also possible in case of solid, and later with the help of thermodynamic expression we can also prove it that yes, if the composition goes to infinite dilution we can get to the ideality. We will prove that later on. Now, interestingly here what we are considering, that we are saying that it can be mixed in the entire region. So, that means we are going away from ideality, means ideality means it has to have a very low dilution, but that is also an assumption that we consider that the entire region the system would behave like an ideal solution. This is an assumption. So, the system would behave ideally. For entire composition regime. So, we are considering into the, we are getting into the ideal system. Now, whenever we talk about ideal system and we consider that it could be either liquid solution or solid solution, and liquid solution and solid solution means when the solution form is liquid as well as the solid solution means the solution form is solid. Now, when we do that, we have to also consider two more external parameters. One is temperature, another one is pressure. Now, liquid and solid both are condensed phase. Now, it is very minimal effect from pressure on those condensed phase. For example, in order to change a little volume of a solid iron, you need to go to very high pressure, so that the solid iron pressure can be, volume can be reduced. So, that is why even if we change around 1 or 2 atmosphere pressure, there will be hardly any effect on solid iron in terms of volume change. So, that is what we generally keep the pressure constant equal to 1 atmosphere, and then we consider that we are mixing them at different temperatures. So, that means we have A atom, B atom, and we fix at a temperature, and that temperature could be anywhere. It could be either that temperature could be above the melting point of both A and B, or the temperature could be such that the temperature is less than the melting point of A or more than the melting point of B, or we can choose a temperature where that temperature is less than the melting points of both A and B. So, then we will fix the temperature and form the solution, and then in order to get the temperature effect, we will change the temperature, again the same way we will form the solution. So, that is the treatment purpose, that is the treatment sequence. But when you are fixing pressure, now you must be wondering that if we fix pressure, then people talk about vacuum treatment, people talk about high pressure heat treatment. Okay. So, why those things are coming in? So, now it is important to talk little bit on the pressure effect. Okay. So, in order to understand why you need low vacuum in case of highly oxidizing prone metals, why you need little positive pressure while treating brass or steel containing manganese, copper, chromium. So, we need to know the philosophy behind it. So, in order to know philosophy behind it, let us get to the effect of pressure. So, I feel that this is important in order to know that particular concept, that when we need vacuum treatment, when we need high pressure treatment, all those stuff. Though normally in case of condensed system heat treatment, pressure effect is minimal. For example, in case of steel, if you are fortunate enough to see a rolling plant, you will not find that it is done in vacuum, it is always done in normal atmosphere, because that entire plant, entire line, the rolling plant could be almost about close to 200 meters long. So, maintaining vacuum in order to avoid oxidation of steel is economically not viable. So, that time we always operate at normal atmosphere pressure, but there are situations where we do need to worry about pressure. Now, let us get back to the effect of pressure. So, now when we talk about effect of pressure, then we have to take help from one particular thermodynamic equation. If you have seen this, I think you have seen this equation, which is one of the famous equations of thermodynamics. Basically, from this Maxwell equations can be derived, and these equations are basically based on the equilibrium concept. Now, I can consider solid and liquid, these two phases, and if I try to see what is the equation, this equation form in case of solid, I simply write dg solid equal to V solid dP minus S solid dt, and where S is the entropy and V is the molar volume. Similarly, in case of liquid, dg liquid equal to V liquid dP minus S liquid dt. Now, if there is an equilibrium between solid and liquid at some temperature and pressure, then these two quantities for infinitesimal changes, these two quantities will be same. since if they have reached equilibrium, previously we have seen that if we try to see the effect of temperature, pressure is constant. We have seen that the curve look like this, and at this point this is G solid, this is G liquid, and this is T melting point, and at this point I see Gs equal to Gl. That is the equilibrium concept. Now, these particular thing can be written in the form of infinitesimal change. Once we do this, then we can write it as Vs dp minus Ss dt equal to Vl dp minus Sl dt. We can write it. Now, if we take the pressure term on one side and the temperature term on other side, we can write it as Vs minus Vl dp equal to now again I can write now here you see in case of thermodynamics what we experience, that final state minus initial. So, this is the transformation when some transformation is taking place. So, we say that quantity at final state and the quantity at the initial state, that difference is counted, because the state functions like G, S, H, we cannot get the absolute quantity. So, we get the relative, the change. So, whenever we write that, that means the transformation is taking place like this, initial equal to final. Since it is written S minus SL, so that means transformation is taking place from liquid to solid. So, this is my initial condition and this is my final condition. So, then I can write it as liquid to solid and where this quantity is solid. So, now this equation is valid at equilibrium. Now, we will get to this particular equation after a while. Now, first consider these two equations. So, now dGs equal to Vs dp minus dt. Now, if I try to see the slope at constant temperature, then it would become Vs. Can we get negative volume? Never. So, that means this volume is a positive quantity. So, if it is a positive quantity, if I try to measure, try to see the variation of free energy with pressure at a constant temperature, it would always have a positive slope. So, if I try to plot that variation with pressure, I will get a plot like this, which is G of solid. And now, in case of liquid, this is solid. In case of liquid, I will see dG liquid equal to VL dP minus SL dt, then dGSL dP T equal to VL. VL is also a positive quantity all the time. Now, it would also have a positive slope, that means free energy change with pressure at a constant temperature. So, that means T is a constant. Now, in case of water, if we consider liquid as well as solid, that means ice. Now, if we see the molar volume of water and ice, that means the liquid water and ice at 0 degrees Celsius, when the pressure is 1 atmosphere, water has got molar volume of liquid water is less than molar volume of solid water. So, now if I compare this is, if we say ice and if we say this is liquid water, this one would have lower value compared to Vs. So, that means VL is lower than the Vs. So, the slope of that free energy change of liquid with pressure would also be low. So, then I can say that this is GL for water in case of water. So, now that time we are considering, if we consider this is as 1 atmosphere and if we put it as 0 degree Celsius, then they will match at 1 atmosphere pressure. So, that means this is the equilibrium point. So, hence if I increase the pressure at 0 degree Celsius, then ice would melt. So, that means if I increase the pressure this way, I see that ice is melting. Why? Because the free energy of solid is more than the free energy of liquid. That is why ice melting is easy, because free energy change goes to negative. So, now coming back to this particular equation, if we treat it further, we would get to see an interesting phenomena, and that phenomena relates to the fact that why ice melts if we increase the pressure, and why if I release it, then again it solidifies. So, that means we are getting into the terrain of Clapeyron equation. So, we will stop here. So, we will continue in our next lecture, where we will talk about Clapeyron equation as well as Clausius Clapeyron equation. Thank you.